Okay, so today we're going to be covering the DeepSeek V3 tech report paper. I'm specifically going to be focusing on the innovations that they talked about through the DeepSeek V3 base model. And I'm going to be only briefly touching upon the GRPO and the DeepSeek R1 stuff, which is the reasoning model that you use when you go online to deepseek.com. And then I'm going to talk about some of their newer stuff, which is inference time scaling for generalist reward modeling. That is, I think, some of the coolest stuff that's come out recently. And this is all one gigantic paper. So just quick show of hand. Has anyone read the paper? One in back. Awesome. Oh, kind of read it. Skimmed it? Okay. Well, skimmed is better than everyone else because you actually rose your hand. So we'll see. Feel free to ask questions as we're going through this. The whole point of this talk is more to go over what are the cool innovations that came out of DeepSeek that are currently advancing how LM and AIs powered by LMs are going. They produced quite a bit in a short order, and it's less about that particular paper because that paper is kind of a summary paper of like 3 or 4 papers all combined. All right, so first, before we get started, who the heck am I if you haven't been here before? And, oh, right. Okay, I'm Keith. I am a individual who loves AI and tech. I routinely run the paper club here. I usually do the presentations about 50% of the time, and the other time I set it up for whoever else is actually doing it. Welcome if you're here for your first time. I also do a lot of SDx events here, not running it, but I just attend it. So if you see me in the community, come say hi. I'm super interested in robotics and AI. I have a website, hlfshell.ai, which I believe this guy will take you to. That is where I write about tech, AI, stuff like that. You can also see a lot of my project work. And I'm currently working on a agentic framework in Python that's kind of AI agentic tools for makers. So if you're interested in that, feel free to check it out. Let me know if you're building anything cool with it. I will also say that the slides have already been posted to the Discord in SDx. If you're not in the Discord, you should definitely join up. I'll give you instructions at the end how to join it up. So just let me know. Let's talk about the DeepSeek V3 innovations. First, does anyone here know what DeepSeek V3 specifically is? Has anyone used it?
The base model for R1?
Yeah, it is in fact the base model for R1. So it is an instruct-based LM model, but it is not a reasoning model. It's the R1 model that kind of caught everybody's attention, but this is still a very good, very large model. It is a mixture of experts model, 256 experts per layer, 8 activated per token, and a 671B parameter model. So it's quite large and quite cool. What they managed to do, though, is they created a number of innovations within how it performs inference and how they trained it to greatly increase the efficiency of these models and kind of change the landscape of training LLMs. Specifically, it specializes in coding and mathematics, and I'm actually going to come back to this later and say, why is it necessarily good in coding and mathematics? That's actually a trend you'll see across a lot of models, and it's an important thing to note. Think on it while we talk about everything else. It's open source, which is really nice because OpenAI doesn't actually present open weights or open anything for their work, except for the occasional research paper. And it has similar performance to GPT-4o, depending on what the actual task that you're doing at hand is. So this is fantastic. This means that you can go download this model right now, install it, run it on whatever hardware you can. I don't know if you happen to have enough hardware to run a 671B model. If you do, that's awesome. But you can go and use it. And it took $5.6 million supposedly to train, which GPT-4o took somewhere between 60 and 100 million, depending on what your sources are. Sam Altman himself mentioned it probably took over $100 million. Now, some people say this $5.6 million isn't accurate because it doesn't include researcher salaries and everything. But the point is you're still an order of magnitude or so lower than the competition. And we're going to talk about how they managed that. In fact, this is from the paper itself where they talk about in US dollars, they spent $5.3 million pre-training and just post-training $10,000, which is cheap. I can't afford it, but it's cheap for these companies. And this one table was so prevalent in the news that NVIDIA really didn't like that day. They lost $560 billion in one day because of this paper. They gained a lot of it back because of the hype, but they definitely, this paper turned some heads and got some people very interested in what the hell these people were doing to manage to get around the hardware restrictions we put on them and completely prove that you could train these models for millions instead of hundreds of millions. Oh, and as Corlin mentioned earlier, it was indeed the model that DeepSeek R1 was built off of, which I'll mention a little bit more later. As I said earlier, I talked about DeepSeek R1 in an earlier talk. This QR code will take you to an article I wrote about it and a video of me doing a presentation on it. So while I'm only going to briefly talk about it tonight, if you are interested, I do a much deeper deep dive there for R1 specifically, so you can get a full walkthrough of how that's trained. All right. And yeah. Oh, and they implemented something called MLA for efficient 128K token context. So this is 128K token context, means you can have up to 128,000 tokens in the context at once. That's including the output tokens. So how do they manage to train and create a super efficient model with such huge context, especially when they're hardware constrained? Let's cover that bit first before we dive into the more complicated training stuff. So who here knows what MLA is? Anybody? Yeah, hit me.
That was actually one of the things I wanted to learn more about.
Okay,
I
well,
knew it was different from the original transformer architecture. It was a way that I understood it. It impacted like the multi-added.
yep, very close. You got the pretty much most of the gist of it. It's basically a change of the typical way that multi-attention heads work within self-attention. So this is standard attention. This is a chart I took from a much earlier talk I gave on decision transformers. Specifically, this is the typical thing that you see in a standard self-attention head, where you have a whole bunch of keys for your tokens, so you have a whole bunch of queries for your tokens, and then you have values, which is calculated through this formula here. Then you do this across all tokens that you have. Now, this is one of the reasons that LMs are so heavy in VRAM memory. It's because you are growing quadratically. For every token you add to your context window, you are quadratically expanding the amount of memory that you actually need. You may see some versions of this table where below the diagonal, you'll have negative infinities. I've explained this in another talk. That's something called autoregressive transformers or causal transformers, where you don't want the model to look ahead to the future in order to do certain predictions. This is really good for, let's say, translations and for some LM applications. But the point is, this is what you typically see for your head. Now, how can we efficiently increase the context size without, I mean, the obvious way is throw a hell of a lot more VRAM at it, but we're hardware bound and you can't just magically wave a wand and get 300 extra gigs of VRAM just like that. So how could we do this more efficiently? Well, they decided to do something very similar to LoRa, and they basically use low rank adaptation vectors in order to shrink it down. So what they do is they basically take the token hidden state, which is kind of the stuff here that as you're passing it in, you're doing a compression against it, much like you would for a low rank adaptation QLoRa. Who here knows what a LoRa is for training LMs? Okay, cool. Yeah. So basically, all you need to know about LoRa is that it's a technique mathematically in which you compress, you create a series of low rank adaptations, which when multiplied result in the large matrix changes that you need. And then you do this so that you can create small adapters that when applied to a large model, despite the fact being only a few megabytes in size, can change a multi-gigabyte model to the fine-tuned version that you have modified it for. This is how, in the background, all the LMs are quickly swapping between fine-tunes. You can just load a bunch of LoRa's and one base model that they're based out of and not have to do a very expensive model switch every time. They're utilizing the same techniques here where they're basically saying, okay, instead of storing 128 times, because that's the amount of attention heads that this model has, and that times all the keys and the values and the queries that we're doing, we're going to create a single compact latent vector, and then we're going to cache it so we can very quickly access it and then decompress it through multiplication. Queries are also compressed for this process, but we don't store them in memory because those are only needed for the time of that one inference pass. That's a very quick explanation for it, and I know that I could go into much greater depth on the mathematics for it, but I'm going to go straight into the training stuff unless there's any questions. No?
Just a quick one.
Yeah.
Low rank. What's the rank there?
How good are you at linear algebra? Okay. So the rank is a property of a matrix. By having a low rank matrix, you're basically saying that it is a smaller matrix overall, and it's going to, yeah, it's related to the matrix properties.
Sorry, just want to add one thing quickly because I think it is like a little bit. So with LoRa, I don't know actually about how this works with the compressing the vector. But the LoRa, the general idea is you have a large matrix. You want to represent it as the multiplication of two smaller matrices. So instead of storing all of the parameters for that big matrix, you just do the ones for the two smaller ones. So you save like kind of like an order of magnitude on parameters.
Mm-hmm.
That multiplication. But I'm curious about when we say compressed latent. I'm assuming this is a vector now. So the low rank for a vector, what does that mean?
It probably has to do with the actual weights bit. So, yeah.
What's this? How does this affect performance?
Significantly. For V3 specifically, they saw, depending on what the calculations you were doing, if you're using, say, most of the context, you can get up to a 57 times increase. More realistically, you're going to be seeing anywhere from 1.8 to 10 times increase in efficiency of memory usage, which is a pretty big deal.
And LoRa is it paper?
So if you want to read more about low rank adaptation, look up QLOR or LoRa. Both are from Microsoft. It is a very common technique that you see in model fine-tuning and model deployments. All right. So let's dive into the actual meatier part of this paper that I'm super interested in. It is the training advancements that we got out of the DeepSeek V3 model. First, floating point quantization. Now, this is something that we've talked in depth about at an earlier meeting where we talked about specifically 1.58 bit quantization and trinary quantization. That was fascinating here, but this was actually, turns out, the first major model to utilize in training floating point 8 quantization during training. It drastically reduces the memory and speeds. So who here is confused by what I mean by FP32 versus FP8? Does everyone have that down? Cool, awesome. So yeah, so we are several times smaller if we're using FP8. However, if you try to quantize down a larger model, you're going to lose precision over time. Now you could decide, I'm just going to train with FP8 from the get-go, but then what happens is that you have less precision when you're doing your weight updates and you're actual passing the gradient through. So even though you're training from the get-go with FP8, you're also going to have less accuracy. So what they do is they basically keep a shadow weight set with FP32, and they use that during the optimizer updates, and then they cast down for forward passes. Now, what they do is they don't do this across every single operation that they're doing. They're specifically targeting what's called GEM, G-E-M-M operations. So anywhere where you see that you're going to be doing, say, matrix by matrix multiplication, you're going to see it get casted down to FP8. But for certain things, like our master weight update, and for some of our other stuff, you're either going to be at BF16 or FP32. So you can, here I'm pointing out that, yeah, it's a mixed quantization during the training. And it was this kind of technique that managed to score out some efficiency without going full in on FP8 or sticking to FP32 for the full time. Specifically for FP8, all the GEM layers, linear activators, weight activation backward passes, and weight backward pass. And then the embedding layers, output heads, and the MOE gating modules, the mixture of expert gating modules that pass it to different experts. Those are all going to be kept at the higher precision, so that way you get the precision on that. And the attention layers are going to be kept there too.
Sorry, what is the GEM layer?
So GEM stands for General Matrix Multiplication. So this is going to be anything that is just two straight matrices being multiplied, or some operation done on them at the GPU level. This is an NVIDIA term. Yeah.
So the whole process of how this works is that you're still keeping these 32-bit floating points in terms of gradients to update the weights.
Yes.
But the model is still an 8-bit.
Yeah, so you downcast as you move forward or do the operation, or during the back passes if it's the right operation for it. So that way you're performing as if you are working at FP8, but you keep the weights in 32 to keep that precision, and then you kind of just get rid of them when you're done. We saw something very similar with shadow weights in the 1.58-bit paper, where they kept 32-bit weights for the model and then discarded them afterwards. All right, So that gets you a lot of reduction in VRAM usage and a lot of efficiency in compute time. So the next thing they did was MTP, multi-token prediction. So this one is basically when you look at transformers, you're saying, okay, it's going to predict the next token, which we're going to say is X time plus 1. And then it goes ahead and predicts the token after that, and then the token after that. Instead, we are going to be trying to predict multiple tokens ahead. So xt plus 1, plus 2, plus 3, plus 4, so on and so forth, up to a set range. Now, this is not necessarily unique to DeepSeek. They're not the first people to do it, but how they did the implementation was, what they're doing is they're basically saying, they've created a methodology such that xt plus 2 is created without knowledge of the other tokens they generated. So it does not know about xt plus 1, the token that preceded it, nor does it know about the token that comes after it when it's trying to do the prediction. And they use the causal multi-token loss to try and force it to do an autoregressive backpass with that information, or with that lack of information, rather. Does that make sense? Yes.
I have a question. So is it essentially like a bag of words on the other side then? If there's no, if it doesn't matter order of T plus 1, 2, or 3.
Oh, but it does matter. It just doesn't matter when trying to predict that particular thing.
But if T3 and T2 were swapped, would the loss function be the same in that case?
The loss function wouldn't see it for the, yes, it would matter because it's comparing it to, when you're doing this initial training, you're comparing it to its ability to repredict the text from your data set. So if it predicts the wrong word 2 down, it won't match your set and it will notice it. And if you swap the order, it will still notice it. Any other questions?
So it's learning some weird things, like instead of predicting the next token, predicting 3 tokens down from the next token.
Yep.
In isolation.
Now, is there anything cool that you can learn from that?
Well, yeah,
as a model?
That's kind of speaking back to your mathematics and coding.
Yeah, and not only that, it also teaches the structure of like language, the structure of what you're doing, structure of code, the structure of sentences, how someone would speak. You can pretty well guess in code that you're going to have a semicolon eventually, and then depending on what kind of timeline you're doing, like if it's a for statement, you can predict there's going to be a colon or a bracket there. This basically teaches the model much quicker about the actual structure of what it's talking, and you see a 1.8x inference speed up with speculative decoding after the fact because the model has been trained to do this advanced token prediction. You're basically skipping several computation steps. And this right here, they're saying they have an 85 to 90% token acceptance rate. What that means is that when they are utilizing the speculative decoding on the inference run, they are basically saying it's right 90% of the time, that this was what it would have done anyway. So we're now skipping over that computation. So super speed up on the model itself.
Is that similar a little bit to like masking during training, where you can sort of like increase generalization by like hiding parts of the input?
I think not, because it's fundamentally changing what's being processed. With yours, you're basically saying we're going to make it more general just by modifying the input and prove that it generalized in order to recreate the missing pieces. This is more saying I'm training a model that's typically producing just one token at a time to train predicting multiple tokens based on the current structure.
Yeah, but if the T+2 and T+3 tokens don't see the ones immediately before them, isn't that at least a little bit like, okay, like if you want to predict 3 tokens ahead, but you don't know the immediate 2 before that, it's like it makes it a harder problem during training.
Yes. Yes, in the back.
There's no win. Is it like a window size whenever it completes the slots? Is that n, or is n like 120?
I do not know the window size. I think it's only a handful of tokens ahead. But I do not know off the top of my head what token size they actually do. It would get very ridiculous very quick. I think it's going to be closer to the 8 to 32 range than 128,000. There's another question in the back?
Yeah, how does it actually output those n tokens, right? The model can only output 1 token. That looks structural.
That's a great question. I suspect that I do not know off the top of my head for that one, but I suspect what it's doing is it just basically calculates the probability of those tokens being chosen and then outputs it. It probably something to do with the output portion of the model? Not sure.
Yeah, because if you can get it to spit out the next n tokens faithfully, then you would think that inference would speed up drastically too, spitting out input at the time.
Yeah. So I do not know what the architectural change for the speculative decoding would be. But look up speculative decoding online and you'll probably find some pretty interesting papers on that subject. All right, any other questions before I move on? Okay, so the next part is the dual pipe training framework. This is the part where they actually saved all the money. And this is the part where it's like, damn, okay, they really knew what they were talking about. So in order to understand dual pipe training, first we're going to talk about what's so hard about training. There's a large scale model training is freaking hard. You need a huge amount of GPUs utilizing at once across a gigantic data set, the sum of all human knowledge, in order to train these things. So doing things that are across all these GPUs are super expensive. And this is especially true on mixture of expert architectures. So I'm going to show you a, oh yeah, it's to the point that on traditional training, before this paper, you'd spend as much compute time on communication between nodes on GPUs as you would actually calculating on the GPUs. So that means 50% of the time your GPUs are essentially idle. That is ridiculous. So they came up with a solution where they created scheduling microbatches. All right, this is from PyTorch. This is a typical diagram of what they call the bubble problem on multi-GPU problems. So we have devices 0, 1, 2, 3. These are the 4 GPUs in your node. This is time as we go to the right. And these are the layers that the GPUs are actively working on as we go through time, right? So we start off with the initial, when you do a forward pass on a model, you have to start at the start. So we start with just the first layer and we do that processing. Then we pass it off to here and we start doing an additional processing of the next layer, the next bit of input, while device 1 is working on the next layer of that model, or the next pass of the model for that initial 0 input. So this is all 0 input here. This is the secondary input of 1 here, third input here. And something happens over time is that you realize that we have what's called the bubble, is that you have to get to a point where you can no longer do additional processing because you are waiting for these outputs to occur to start your back pass. And then only here do you have every single GPU being utilized at once. And you do this over and over and over again as you get to the point of working on your model. So it's only here and then at the actual update step when you're doing the optimizer update, are you utilizing all your GPUs? This times all the GPUs in each node gets ridiculous, which means you have a lot of idle time for all that compute you bought. They created a very overwhelming chart to describe what they're basically doing. This is super complicated, but just bear with me here. Again, we have the 8 GPUs that they are in each of their nodes. We have time going forward, and they nicely color-coded this for us. So basically, blue is our forward pass, purple is our backward pass, and sometimes you see mixed where it's doing 2 different things at once. That's specifically to their application. Focus now just on the blue portion with me. So device 0 gets the start. Just as before, we see a similar bubble. That start basically says, okay, let's start passing through the layer, and we see it being passed down. And just as before, we start to see the next bit of input get passed in, but then we start to see it jump around. And then we also start to see backward passes being interlaced with the forward passes. What they've built is a very fancy scheduler, which basically utilizes the maximum amount of compute time on the GPUs. Now, the big question is, well, how did they pull this off? Well, first, I'm going to talk about NVM-Link and InfiniBand. Has anyone here heard of these 2 technologies? Okay. So NVM-Link is basically the name of the connection between GPU nodes within the same system or the same rack. So if you think of like a singular supercomputer with like 8 GPUs on it, how they communicate between each other, all those GPUs and passing data, that's NVM-Link or NV-Link. And then InfiniBand is basically a high-speed networking protocol that goes between machines with multiple GPUs. It was a separate company. NVIDIA bought them about a year or 2 back. Now, why knowing the difference between these 2 are important? Well, it's because of speed. The InfiniBand, super fast, 400 gigabits per second across the link. But NVLink is achieving 900 gigabits a second across multiple communications at once. It is so much faster that latency is measured in nanoseconds. So we're an order of magnitude faster when we're doing that. So what DeepSeek basically said, okay, we're going to use NVLink whenever we want to use NVLink whenever possible, and we want to avoid InfiniBand whenever we have to. So how do we utilize that? How do we do that? Well, this is a streaming multiprocessor. Your typical training GPU right now has somewhere neighborhood of just over 100 of these in it. And it's basically an all-in-one setup that does a whole bunch of processing that's way more complicated than I can explain to you. But this bit here, the tensor core, is what's doing all the fancy work. What they discovered is that when they were utilizing InfiniBand, when that bubble was occurring or when they're trying to get all these layers and data processing together, all the SMs are sitting completely idle. So that means that they're being super inefficient about it. So what they decided is they assigned 15% of the SMs to do the communication work to kind of deal with all that scheduling that I just showed you earlier. And by just dedicating 15% of the stream multiprocessors to the actual process of communication, they saw a gigantic speed up because it's way quicker to do that over NVLink than it is over InfiniBand. So in order to do this, you might have seen, who here saw a bunch of the paper or newspaper headlines that said DeepSeek got rid of CUDA, right? That was a super popular hype headline that was being passed around. Here's what actually happened. They said, okay, CUDA is a high-level programming interface, but it can't do what we want to do here. So instead, they just use something called PTX, parallel thread execution. CUDA compiles down to PTX. Think of it like how C goes down to assembly code. Think of it like that. They basically said, okay, we're just going to get some super good hackers, and we're going to work directly in the PTX infrastructure, and they're specifically targeting the L2 cache. And the result is, this is because we, hardware bound them and artificially compute bound them from that. They had to do this, or otherwise they would not be able to compete at all. So the result is that they were able to do what is called cube parallelism. They basically avoided tensor parallelism, which would depend heavily on the InfiniBand, utilized this scheduling technique through the PTX coding, and they basically data parallelism pipeline, which is you basically break your data set across the data set. So you have your major batch of all of human knowledge. You divide that down to sub batches of like, a couple million documents, and you pass that around to individual servers or server clusters. You have pipeline parallelism, which is where you start to have different part operations being passed around different machines. And now we have expert parallelism, which I didn't mention before because of how complicated this gets. But earlier when I showed this chart, you might assume, like I did at first, that, hey, oh, this is just going to be a single layer pass with a single set of data. It's not. This is actually an individual expert of the 128 experts that they have processing a single subset of data across a single set of the sub pipeline. So they have managed to get it so that each GPU is maximized because it's such a small portion of what you're actually processing during normal training. And all those things together result in a gigantic speed up. All right, that was a lot at once. But the big thing to take away is that they created so many innovations about training these things that they made it super efficient. They made it much more stable, so they didn't have to spend money to continually redo experiments in order to try and find where they introduced an instability. And they managed to do it all at a budget cost orders of magnitude smaller than their competition. So lots of ideas all at once. A lot of brilliant people coming out with stuff with that. Questions?
Go back to the scheduling slide. Sorry.
Yeah, this took me hours of looking at to try and figure out.
What are the numbers on there?
So the numbers are basically an individual batch for that expert. So we have a micro batch of data from a singular batch, and it's being passed to a specific expert, which is running on this device. So 1 is the second batch, 2 is the third batch, 3 is so forth.
Blue is forward.
Pass. Purple is our backward pass.
What is backward?
So this is confusing, but basically there are times where you're going to see a small purple square. Let's see if I can find one. Over here, notice how it's smaller? That's a specific thing for an optimizer update. I don't 100% follow it, but that's as much as I figured out. So you have backward for weights.
There's backward for input and backward for weights. Backward passes, I guess. Whether it's the first here right after the input or
I think so, yes. Yes, this is a very complicated chart. I will admit that.
My other question was about the InfiniBand. Like, is that all that stuff you were just talking about? That's all in software. Or is that like hardware?
This is hardware.
When they say this is hardware.
Yes.
So is that like an optical link, or how are they actually getting it to go that fast? Like, what is
I do not know what the InfiniBand tech is, hardware is specifically. I just know that it's designed to do specifically GPU networking across data centers.
So the NVLink is 900 gigabytes per second. So it's actually like 20 times faster than gigabits.
That might be a typo, but it is based on the order of magnitude. It's quite possible.
Go back to the slide where you're talking about flow points.
Check me on that, Corlin.
I will.
There was the architectural diagram of
This guy.
that right there.
Okay, I think they're both gigabytes.
Okay,
Like a little over twice.
Yeah.
I was wondering if that.
but it can do 900 on multiple nodes at once. And what, so you were wondering about this, what?
I was wondering if that backwards input versus backwards.
Where am I looking here?
I'm not sure.
Oh, okay, I thought you were saying here you saw it.
No. There's typical backpropagation. You backpropagate.
Oh, I see what you're saying, because the two different back passes would be needed for two different quantizations. Okay, yes. That's a good theory. I do not know if that's correct, but I like that theory. Okay, any other questions on the V3 stuff before we move on? Yes.
When you are, I don't understand how, or I'm not familiar with how multi-token prediction works at inference.
Sure.
Is it done like, can you just walk through it? So you are generating a group of tokens, you then just skip past them and assume they're both good?
There's a secondary model or technique that selects whether or not the tokens generated fits based off the 0th token that gets generated, whereas the 0th is the next token in line. So then you do some kind of calculation or model check on whether the future ones are going to be utilized.
And so then you slide forward one token at a time?
Yes.
And look at the next series
Yeah.
of them? And
So if everything went well,
someone get thumbs down and then you predict.
yep, and as soon as you get a thumbs down, you stop with the branching and you just start. Yep. Okay.
Parallelism. You said that there's no tensor parallelism anymore. Does that mean no cross nodes through the InfiniBand, or does that mean do they not do?
So tensor, let's define tensor parallelism. Let's define that first. So basically, tensor parallelism is that an individual tensor is too large to fit on an individual device, and you have to spread it across. They're basically saying they're avoiding this because it's too expensive to do that, which is why they went to micro batches and why they went to one expert per device.
Device here, is that like a group of 8 GPUs or a single?
One device is one GPU. This is all one 8 GPU server. Yes.
What are some resources? I honestly, this is such a fun thing.
I mean, so PyTorch has a great set of documentation, and so does TensorFlow, I'm guessing. I've read the PyTorch ones, though, that talk about the techniques of training very large models across multiple GPUs. There's some books on the subject, but I haven't come across any that I particularly like. Has anyone done large-scale model training that they want to share some resources? No? Okay, so there you go, Hugging Face. That makes sense. They're pretty well tuned into model training. It's so many people are utilizing the models without doing the training nowadays, especially with so many open source models at this scale, at this quality, that a lot of people at best are doing fine tuning, which you don't need as much parallelism and you don't need as much compute for. All right, I'm going to move on to the next bit. Now, DeepSeek and GRPO1, DeepSeek R1 is their reasoning model. It's what currently is on their website. Again, I said earlier that I did a whole talk on this a month ago and did a little article on how GRPO works. So I am going to go over GRPO briefly in this talk, but I'm not going to cover much about DeepSeek R1 otherwise. That being said, I do want to open the floor to see if anybody has questions or particular comments about DeepSeek R1 they want to say before I move on to the next bit. So Anybody? Has people been using DeepSeek R1 for anything? Played with it at all?
I was confused about this. So R1 came out before V3. R1 is based on V3.
V3 came out first. The paper came out first, but V3 was internally done first. DeepSeek R1 is trained on a technique where, and I will cover this very quickly later. DeepSeek R1 is basically a fine-tuned version of V3 off of a reinforcement learning created data set specifically built around reasoning outputs for examples. Make sense? Yes.
Like, so for reasoning models, all of the like the data set
Mhm.
is just a process of having the LM explain.
To a
That would
point.
mean what reasoning is.
So naively, you would say, okay, it's just a matter of fine-tuning the model on a whole bunch of examples of reasoning. But realistically, in order to get to the point that we are now, the big jump was utilizing reinforcement learning to enhance that process and get it such that the model is being trained towards maximizing reward, where reward was defined as actually doing the reasoning process.
Yeah, but I guess like a plain more plain questions like what's the difference between chat
Specifically how they're trained.
or like physically when I use it?
You will not notice the difference. What's happening in the background is that the model has been trained to spend more tokens on the actual chain of thought process.
Okay,
And the primary delimiter is how they're trained, which I go into more depth here. Good questions, though. Anything else? Yes.
Just on the top of my head, was that the idea that the full parameter version of DeepSeek R1, well, basically the lesser parameter versions are not, there's something I heard where like the full version is the real deal and everything
Yes.
less than that is trained in a different way or kind of.
So the smaller versions, DeepSeek R1 was particularly important, not because of the model itself, though the model is certainly very cool, the 671B one, but it was the set of techniques in which they proved you can utilize just reinforcement learning to very quickly generate a data set that would normally cost hundreds of millions of dollars in human labors to create. So the smaller models that you're thinking of are actually other open source models that are like 7B, 14B, or like 30B or something, that are then trained with that methodology to prove that you can get reasoning model capability out of small models utilizing this technique, which you wouldn't be able to do earlier because with smaller models, you would run into a lot of problems with training on the additional data.
So the 768 was trained on the lower ones were trained on.
Yes. Good question. All right, we're going to talk about generative reward modeling. The paper's labeled generalist reward modeling, but the actual technique is called generative reward modeling. Just saying that now because you might realize that you're about to give a presentation and type the wrong word into a couple titles. And we're going to talk about SPCT, which I guarantee you, at least on one slide, I have switched those letters around without realizing it. So let's see. This is the paper in question that I'm going to be covering. It is part of the V3 technical report, but a separate paper goes into greater depth here. And this is one of the things that really excites me. All right, so I'm going to go through a couple slides that I went through in a very quick talk, specifically on overcoming alignment in LLMs, when I had to train the audience on, well, okay, how do you normally train an LLM? I just wanted to do that real quick so we have a solid basis. This is not how you trained DeepSeek LLMs. This is how you would train, say, ChatGPT 3.5. So first, you steal as much content as possible without paying for it, right? You pirate every book, you take the internet, you take all the hard work of underpaid artists, you collect that as quickly as you can, all right? You hoover it up. Now, we have to move quickly because we're gonna get sued because of this. So you take all that data and you train the best word predictor that you possibly can. The initial pre-training portion of an LLM is you're not training it to write a haiku when you request it. You're training it to, given this subtext of this corpus of text, predict the next 50 words or predict the next one word. And you do stuff like that. So you get it to be as good as you possibly can. And then we would go through the alignment process. Now, traditionally, this meant supervised fine tuning, where we have a whole bunch of prompts created by humans, which basically say, okay, write me a haiku about this now, and have the output of the prompt be a haiku. And then you basically get a whole bunch of humans, underpaid workers, in which to write this and to kind of compile it. And you create a nice little fine-tuned data set, and you fine-tune the model on that specifically. Then you use something called reinforcement learning with human feedback, which is where you take the prompts, you have the model that has been fine-tuned on this, generate outputs, right? You take those prompts, you pass them into an underpaid human labeler, which says whether or not it did a good job. That produces a signal, which then trains the model into the point that it gets instruct, and now you make enough money, you don't have to worry about breaking the law. All right, that's how it's traditionally typically done. DeepSeek R1 doesn't use RLHF, it uses specifically reasoning training through a reinforcement learning thing. Again, I talked about this in depth earlier, but all you have to know is that you take basically DeepSeek V3, you take a whole bunch of chain of thought curated examples. This is just the data sets that's been created. You take that and you train a model on that. So this is now a fine-tuned model on this. We'll call that a checkpoint. Then you take that and you pass in a bunch of new curated reasoning prompts it hasn't seen before. You have it generate multiple outputs, which then is judged by both an AI and human beings in a process called group relative policy optimization, which skips a lot of the problems with reinforcement learning. And then from those responses, you do a rejection process where you reject any bad responses, and you overall take the voted best, use that as a feedback to train the model, right? And over time, you create this reinforcement learning model that has generated a ton of reasoning outputs, which you feed all together into a data set, and you take that and you fine-tune this original model on. And the result is you get DeepSeek R1. You get a reasoning model. Again, I go into much further depth about a month ago. Just go online and watch that video, but I'll happily answer questions about that later. So that is the basis for what we have here, but there is a problem. Yo.
When you say reasoning, like chain of thought example and reasoning prompt, like, do you have an example of what that looks like?
Have you read the chain of thought paper or have worked with that? Yeah.
I know what chain of thought is, but I haven't read it.
Okay, so like chain of thought is basically just express your thoughts, whereas reasoning is a whole bunch of tasks that's going to bite me later. A whole bunch of tasks in which it's going to use reasoning and expresses a chain of thoughts, then does its output again. So it's basically using chain of thought within it. This, if it's a Venn diagram, reasoning is basically inside of chain of thought, but it has some other things outside of it as well. Make sense? So it's like a prompt that when it answers, utilizes chain of thought in which to generate its thoughts, then generates additional things on top of that.
So the preference pairs, because I'm assuming this is similar to RLHF, you're generating like preference pairs that then get ranked, right? And that's the whole idea that the reward, like which one of those two is better.
Yep.
Sort of skip
Except we're doing it across a large group. Yep.
Yeah. And so in that case, like the favored response would be like a prompt that is more like goes into its explanation deeper or something like that, or
Yes.
okay. I was just trying to like imagine like a good example of that and a bad example of that.
So when you go through the DeepSeek R1 paper, they specifically studied a couple different things they could reward it for, but what it came down to is the only things that were stable was, does it follow the structure of doing the reasoning and then answering, and was it correct? That's literally the only things.
Doesn't matter if you got the right answer.
Yes, pretty much. Yes.
Feel free to say this isn't the video or whatever, but you said that this process avoids some of the problems with RELF or whatever.
RLHF, reinforcement learning human feedback. Who here has worked with reinforcement learning a bunch? Anybody? Yeah, okay.
I haven't, but I did the DPO paper.
You did the DPO paper, so you remember this. There's a common, I do pretty much all the other reinforcement learning talks at this place. I've done a lot of reinforcement learning, especially for robotics. And the number one thing you need to know about reinforcement learning is that if it's possible for you not to use reinforcement learning, do that. Always avoid it. And the reason for is because when you're doing backpropagation on typical models, you're taking a reward or an output or an error or something, and then backpropagating the difference between what you wanted and what you have back through the model in which to make it more accurate. Reinforcement learning is what you utilize when you do not have a mathematical relationship between the output of what you generated and a way to backpropagate it, unlike an error. A good example would be like a robot throwing a basketball. I can't really create a mathematical formula for the things that it went through to finally throw that basketball to feed back into it, except for 0 or 1 if it made it, right? And so reinforcement learning is a set of algorithms and techniques in which to translate that unconnected mathematical outcome back through the model to propagate. RLHF used PPO, proximal policy optimization, which I've talked about in depth prior, And it's a very good algorithm, but it has instabilities and there's a whole bunch of issues, and it's not as efficient as directly having a reward signal. Now he mentioned, Paul here mentioned DPO, which is direct preference optimization, which was one of the first big advancements about a year ago. He presented that paper, which did a pairwise comparison between two choices, and that created an actual mathematical direct connection. So we could cut out PPO and create a reinforcement learning, cut out the reinforcement learning, and the result was, hey, this is way more efficient. Make sense? So GRPO is that process here where you're doing multiple responses, something around 8 responses per prompt, and then just kind of ordering them. Okay. Did I answer the question, or did I go off to a bunch of rant?
Yeah.
Okay, good. Okay, so this is DeepSeek R1. We can come back to this later, but we now have a basis of how models are typically trained, how DeepSeek R1 was trained. Now let's talk about specifically the problem. I said earlier, DeepSeek V3 and DeepSeek R1 are both good at coding and math. Can anyone tell me why? Exactly. It's very clear when the answer is wrong. We can very easily label an output from the model a comparison between pairs. Well, this one works and this one doesn't. So you could argue that coding test is a little bit ambient, but you can, in the end, run a test and say, yes, it produced what I wanted, right? But you can't say the same for a poem. You can't say the same on, say, a discussion of political topics. You can't say the same for a deep research dive into a particular science topic. So the question becomes, well, if I can reward it with a 1 or a 0, why can't I use in between values? Why can't I just use some value like, oh, it's like 50% of the way there? Anybody? Because it can't scale. It's very difficult to justify why to score something at 50% versus 1 or 0. You know, it's right or wrong is much easier because you just have to set a set of stringent standards, and if it passes that, then it passes, give it a 1. But anything in between gets really difficult, and you actually have to understand the context of that particular prompt in order to do it. And frankly, scaling this is a nightmare. So can we introduce a better scoring method for complex domains? So I'm going to pull an example directly from the paper here. Sorry for blinding everyone with the white. All right, so this is directly from the paper for generative reward modeling using pointwise. We'll talk about pointwise in a second. So the prompt was basically, please help me review for my behavioral neuroscience exam by giving me the core information that is essential to this course. Please give me an expansive review and include explanations and analogies and metaphors. There is no way in hell I'm going to produce a mathematical equation to figure out the best way to guide this. And it does produce an answer, but the question is, how do we now reward the model for being very particular towards the instructions we gave it for that particular prompt? And well, let's say that we had this technique for rewarding it, right? So let's say, okay, well, we're going to create some specific criteria in which to judge this specific prompt. The depth of the analogies and metaphors, okay, we'll weight that 30% because that was one of the things they specifically mentioned. Comprehensiveness of the core information, we have to make sure that they're doing a thorough review as requested. Clarity and organization, well, if it's not clear, what's the point of writing it? We have to make sure we don't confuse the student. And engagement and appeal, well, let's give that a lower weight, but still a pretty decent weight because we want to make sure that it seems memorable because we're trying to help them study. That's a really cool way to do this prompt. And then what we could say is we could say an additional analysis of what we think of the prompt based off what we just read, right? A couple sentences there. And then we could basically assign scores. Okay, well, based off of the criteria that we set, I'll assign a score between 1 and 10. I'll give it a 7 there, a 6 there, a 6 for clarity and organization, and engagement and appeal, we'll give it an 8. And then you can basically say, oh yeah, I could totally just take the weights of what's important to me, multiply that through, and end up with an overall scalar value. Now this is awesome, but it's impossible to do at scale. You would need a human expert on every single prompt, on every single topic, paying them to do this for years, and you still wouldn't have enough data. So why is this being done now? Well, DeepSeek said, hold my beer, we're going to train a model to do this. So they said, let's automate it. They created something called self-principled critique tuning. Half the time I'm going to say the C is here. It is not. What this basically means is they're going to take a two-phase method where they're going to make a model that's trained to do GRM output and specifically train it to generate better principles and accurate techniques and create better and better scoring of different subjects. So in order to do this, we're going to do rejective fine tuning, and then we're going to use GRPO and online training. So rejective fine tuning is we're going to take our base model, like DeepSeek V3. We're going to feed it into prompts, and it's going to generate 2 or 3 or 4 responses. Then we're going to have another model, which is a LLM that is based upon and prompt it to take the input of these responses and then generate the GRM output that I just showed you. If all of the outputs for the GRM agree, we reject the sample because we want it to actually be critiqued. We don't want it to just like everything we pass it. If it doesn't match the ground truth, we do build up a data set of this at first, then we also reject the sample. But the result is that over time, we are building up a data set of GRM, building up a data set of examples and training this model to basically really good at taking the prompt and the output and generating this GRM reward modeling. So once we have it produced, we can utilize it in training of another model such that we can produce multiple critiques per response and combine them to create even better signals, specifically using score aggregation. So off the bat, you'd be like, okay, well, if we did create like multiple responses because it's a stochastic model and then try to basically say this response here rated at 6.7, this one at 5.2, this one at 3, how do I choose what the overall score is for the feedback on the loop? You could say, well, I'm just going to take the average of it, right? What could go wrong with this, though? Anybody? That could be one of the things, too. And the other thing is that you could have really bad samples that completely screw up your scoring, either with way too high or way too low. That's separate from everybody else. So, and some of the critiques might not be accurate at all. So what they do is they basically use something called meta-RM filtering, which they train yet another model whose sole job is to take the text input of the GRM output and then create a small scalar reward that just judges the GRM critique. So you do that for all of your critiques and you get a scalar value for how accurate that critique is. And then you can just take the top N critiques and then average those together.
How do you know that scalar reward model is good though?
Data set and lots of training.
Sure you don't need another model to tell you?
This is like LLM as a judge on top of LLM as a judge.
Yes, it's actually, when I read this, I realized that it's actually just a really fancy actor critic, which, who here has done actor critic reinforcement learning before? Anybody? This is just a fascinating idea of just models training other models, but yes. So what does this mean? This means that you could basically now take a prompt, feed into the base model that you're training, have it generate multiple responses, have that trained GRM generate the response of how we're going to score it, possibly have meta-RM check the values as well, take the top responses, get a score, feed that into GRPO to train the model, feed that back to the model, and this model is now being trained by this guy. Now the fun part is, once you train this guy, he just takes text input. It doesn't have to be the same base model. You can do this across any text model now. So it doesn't even have to be the same size model. If you train a good GRM model, this could be a 7B model or a 671B model. You could just swap it out. Your training technique is now going to be the same across all of them. So this is a highly advanced actor critic approach, and I absolutely love this and got excited for it. That's why I picked this paper. So any questions about GRM specifically before we move on?
There's some how well it works.
Oh yeah, there's a whole paper that goes into the evaluations of it. I just had to cut a lot of that stuff out to keep in time. The particular paper I linked back here is specifically goes into all the pros and cons of it. That one. So that particular paper, and again, the slides are in the Discord for you. This is generalist reward, inference time generalist reward modeling. And they're basically using it to create models that are better at non-standard domains. And by that, I mean not coding, not math. So if you can train a GRM model that's really good at critiquing, say, science papers, well, this is how you can train a model to be really good at writing science papers. All right, any questions on GRM? Any questions in general?
So I guess the concept here is that the way that this would have to work is that building a critique model is somehow less trivial, somehow more trivial, easier than building the base model itself. Otherwise, what are we even doing?
So remember that this base model is still pre-trained, which is difficult to do.
Right.
All right, but once you have a general
You just
generative
have to
reward
build
model
another
created,
to make
yeah,
your original model better.
Yeah.
The assumption then is that making that whole other model is less effort than making a model in the first place, right?
yes, and it also has the benefit of being flexible, of being able to train multiple models.
But like that model also has to be like better than the other one, right? Like what would happen if you use the base model to like create its own responses? Why would that be worse?
Probably because it's not what we're specifically judging it on. So what we're judging this model on is we're trying to create a methodology in which to judge this to perform the task that we give it, because it's instruct based. Could be reasoning, could be not, but the point is that we want this model to do the task we gave it. This model is highly tuned only to generate this kind of output. And we have ways to judge based off the prompts what we would expect it to say are the criteria that it should be judging off of. And we can judge it specifically on how accurately it scored it compared to what we want it. So it's fine-tuned specifically to that. This is like how when you highly specialize a model, you lose some general knowledge. But if you also highly train a model for every domain, you're going to lose some highly specialized
So
stuff
they
as
use
well.
those for specific criteria, or did they use different ones for different
They judge it based off its ability to generate what criteria it should judge a given response on, and it's fed the prompt of what it was requested. So it has to come up with these criteria and what to weight it and what to score on it. And the analysis is basically the equivalent of chain of thought, where share your thoughts, where it talks about it prior to the scoring.
The magic of like back when they developed GANs, right, was this idea that it was a really simple problem at its core, right? It was try to fool this other model that's going to sort of train each other as you go on.
Yep.
This is completely separate from that. Put in all of the time and effort to make as good a model as you possibly can. Force the base model. That just seems like an incredibly difficult thing.
But once you have a very good GRM model, you can train a whole bunch of other ones.
They could also probably just fine tune an opening
I mean, I think that's what they did.
Yeah.
Yeah. Wasn't that Keith that they basically used a lot of opening?
So I discussed that in the DeepSeek paper as well. There is a lot of speculation and claims and questionable evidence. Yes.
So I guess I was maybe a little confused on that. Are these what the principles are?
Yes.
Okay, so basically the GRM model is inherently automate creating based on the available data set that we have.
Yep. So the GRM model says, okay, given the prompt, this is how I would score a response to it. Now I'm going to actually start analyzing the response and generate a score for it.
I think you could bring an opinion to how to build the rubric on the left side.
Yeah.
Score on the right
I mean,
side,
that opinion is expressed through your data set when you train the GRM.
the score on the right side still feels a little.
So if you asked a typical LM to generate scores for something, you will get wishy-washy responses. And that's because it's just not something that that LM was trained to do. But if you specifically train it to do so, then you can get this.
Also, is there what's preventing it from just coming up with one criteria?
You just punish it. You reject it. Or you punish it through the reward signal.
I guess like that in the model.
Yeah. So the rejected fine-tuning here is we basically say we're checking to see if it's the principles, which are the criteria. Yeah. The critique, which is the analysis, and this basically what it's scoring off of. Yeah. So if everything agrees, we reject it. If it doesn't match the ground truth close enough, we reject it. And the result is that you are training it on these good sets, and it learned how to duplicate those.
That's just
Yeah, it's basically a way to stop instability of or reward hacking on the model's point.
We haven't gone through this yet, but I just know, right, the whole point of it was to make it be more scalable at inference time. Why is that?
Can you repeat the question for me?
I just remember because I was going through the paper, it talked about one of the reasons why they did this is to make it more scalable at inference time. Hence why it is more scalable.
I don't know why it would be more. I don't know. Probably. Or you can use a smaller GRM model too if it's highly specified. But I do not know to what they're referring to.
From the abstract that I have open. Furthermore, for effective inference time scaling, we use parallel sampling with meta-RM process.
Ah,
Better scaling performance. It's the meta-RM part.
that's what they're referencing. Okay. There you go. Okay.
The GRM and whatnot, that's just used in training though, right? Like what's spit out is just like the inference time.
So inference time for this model, you would not use the GRM, but you could. Are you familiar with self-consistency? Self-consistency is where you ask the model for a given prompt, generate n responses, and then you can do tricks like say, I'm going to convert all of these responses into vector embeddings, cluster them together, and find which ones group more likely, because models are stochastic. So if the model's likely to get it right, the biggest cluster should be the correct answer. So then you select out of that group the centroid and you find the closest one to that centroid. And then boom, you basically voted on which prompt was best. You could essentially use this for that as well. So imagine like, okay, yes, you're going to train a better model off of that GRM. But you could also have a really good GRM that can then take base model output, check what it did, and then decide whether or not it did well enough to do it again. Unlike, say, the shadow weights when you're doing the quantization or something, this is a model that has actual application outside of the training loop. Okay, any other questions for anything in the presentation? Okay, well, thanks for sitting through and listening to me tonight. This is a link to my website where I do a whole bunch of articles on this stuff and talk about some of my projects. And I'm gonna end the video.